Okay, thank you, Chairman. I'm Mikio Eto from Keio University in Japan. I'd like to talk about flux-dependent Kondo effect in an Aharonov Bohm ring with an embedded quantum dot. And this is the outline of my talk. After the general introduction, I will explain you our scaling analysis for the Kondo effect in this system. First, in the small limit of the ring size, and then I extend our calculation to the finite ring size. So in the introduction, let me start with the quantum dot, a small box of nanometer scale coupled to two leads. So energy levels are discretized in the quantum dot. And with the large charging energy U, so-called Coulomb blockade, you can tune the number of electrons in the quantum dot one by one using the gate voltage. And each peak of the current shows a symmetric Lorentzian shape due to the resonant tunneling through one of the quantized energy levels. And conductance becomes 2e squared over h at the peak, and width is determined by the level broadening due to the tunnel coupling. And let's consider the Coulomb blockade region with spin 1/2. Then the Kondo effect takes place. In the Kondo effect, the spin 1/2 in the quantum dot is coupled to the Fermi sea in the leads and makes the spin singlet state schematically like this. And this is the many-body ground state, and the binding energy is given by the Kondo temperature, Tk. So this many-body ground state makes the resonant level at the Fermi level, and width of the resonance is given by the Kondo temperature. So as a result, at low temperatures much lower than Tk, resonant tunneling takes place through the Kondo resonance. So the conductance goes to 2e squared over h. And in other words, a phase shift accompanied by the transport is fixed at pi half of pi. And size of the singlet state, so-called Kondo cloud, is given by this equation, Fermi velocity divided by Kondo temperature. So it's very large, a few hundred nanometer inside the lead. Okay, so what happened when the quantum dot is embedded in an AB ring, and there is an experimental result without Kondo effect by Kobayashi and co-workers. So using this sample, by changing the magnetic field, they observe the AB oscillation as a function of the magnetic field. And then fixing the magnetic field and changing the gate voltage, they observed a symmetric shape with peak and dip, so-called Fano resonance. The Fano resonance is due to the interference between a discrete level in the quantum dot and continuum spectrum in the leads. And conductance is given by this equation, and Q is a complex Fano factor in the magnetic field. And shape of the Fano resonance changes with the magnetic flux inside the ring. In the presence of the Kondo effect, so we have one-body interference effect, so Fano effect, and also many-body resonant effect, Kondo effect. So this is the theoretical result by Hofstadter and co-workers using this model. And here the phi is the AB phase corresponding to the magnetic flux penetrating the ring. And the conductance shows a Fano-like shape depending on the magnetic flux inside the quantum dot. But in the Kondo region, reflecting the phase rigidity at half of pi, the change of the conductance becomes slow. A similar result has been observed experimentally. So in my talk, I will discuss this Kondo effect in detail. So in the present study, we examine the flux dependence of the Kondo effect using the Poorman scaling, and we obtain analytical expressions for the Kondo temperature and conductance at finite temperatures. First, I examine the small limit of the AB ring, and we show you the large flux dependence of the Kondo temperature. And second, I briefly mention the ring size dependence. For the detail, please see the poster by Ryosuke today. So this is our model. So our model is almost the same as Hofstadter's model. And two reeds are represented by a one-dimensional tight binding model. And we are interested in the Kondo region, where a single electron is localized in the quantum dot. That is, addition energy of the single electron on the quantum dot and also the extraction energy from the quantum dot are much larger than the thermal fluctuation and level broadening gamma. And gamma is given by this equation, and nu is the density of state in the reed. The strategy of our calculation is as follows. First, we diagonalize the two reeds and upper arm of the AB ring, or outer region of the quantum dot. So there are two eigenmodes. So one is incident from the left, partly transmitted and partly reflected, or incident from the right and partly transmitted and partly reflected. Second, we perform unitary transformation for the two modes, so that one of the modes is completely decoupled from the quantum dot. And neglecting the decoupled mode, we make the reduced model with single mode. And this mode is coupled to the quantum dot with this tunnel coupling. So this is the generalization of the paper by Grassmann and Reich to separate reeds. So the reduced model is described by the conventional impurity Anderson model, but the density of states in the reed is complicated depending on the magnetic flux. So this is the density of state when phi is smaller than half of pi, and the density of states is like that when the AB phase is larger than half of pi. So all the information of the interference effect in the AB ring is involved in this magnetic flux dependence of the density of states. And flux dependence is taken into account through this function p phi. Here, alpha is the asymmetric factor of two tunnel barriers, and TB is the background transmission through the upper arm. So both are between 0 and unity. So now examine the scaling analysis using the reduced model. The remarkable properties of the Kondo effects are there is only one relevant energy scale, Kondo temperature Tk, and Tk is determined all the energy scales from Tk to the bandwidth. So to capture the Kondo physics, Anderson's Poorman scaling is useful. Bandwidth d is gradually changed, and we normalize exchange coupling between localized spin and reeds, not to change in low energy physics within the second order perturbation. Technically, we adopt Haldane's two-stage scaling, assuming infinite U. On the first stage, charge fluctuation, so the number of electrons in the quantum dot is unity or 0, and energy level in the quantum dot epsilon naught is renormalized. On the second stage, after the charge fluctuation is quenched, spin fluctuation is taken into account, and exchange coupling J is renormalized. And in the first stage scaling, we obtain the scaling equation for the energy level in the quantum dot. And so this is the renormalized level in the quantum dot. It is flux dependent through the function p phi. So the renormalized level is the lowest when the AB phase is 0 and highest when the AB phase is pi. And in the second stage scaling, we make the Kondo Hamiltonian by the Schrieffer-Wolff transformation. And we have exchange coupling times by J and potential scattering time by K. And J and K are renormalized by this scaling equation. And finally, we obtain the analytical expression for the Kondo temperature. So this is our final result. So the Kondo temperature is strongly dependent on the magnetic flux phi. And conductance can be calculated in the conventional way. At high temperatures, we obtain logarithmic corrections, and at low temperatures, Fermi liquid theory yields the unitary limit and its corrections. So until now, I discussed the case of a small limit of AB ring. But we can extend our calculation to the case of finite ring size. And so we adopt this model. The ring size is denoted by capital L. And similar model has been examined using the slave-boson mean field theory by this group. And first, we make the reduced model with single lead. And in this case, density of states oscillates with this period, Fermi velocity over ring size. When this period is smaller than Tk, or ring size is much larger than the size of the Kondo cloud, Kondo temperature is independent of the magnetic flux. But otherwise, Kondo temperature depends on the magnetic flux. So the detail, please see the poster by Ryosuke today. So this is the conclusions of our study. Scaling analysis for the Kondo effect in a quantum dot embedded in an AB ring. And analytical expressions were obtained for Kondo temperature and conductance. And Kondo temperature is significantly modulated by the magnetic flux phi when the ring size is smaller than the Kondo cloud. So thank you for your attention. Crossover, what do you mean by crossover? No. We take the Poorman scaling method, so we cannot examine the crossover. We need NRG numerical calculations or something. So we cannot examine the crossover region.
This will be a way to measure the size of the Kondo cloud, but not measure.
Well, so our scaling method is applicable when the ring size is much larger than the Kondo cloud or much smaller than the Kondo cloud, but between the regions it's difficult.
Have you mentioned the conductance? Did you show the conductance?
Yes?
Another question. You said that at low temperature you go to the Fermi liquid, but how can you go to the low temperature you do calculation in the weak regime, no?
So you're asking me the crossover between the high temperature region and the low temperature?
Low temperature in this formally.
Well, again, so only we are using the Poorman scaling, so we cannot examine the crossover region. So for the crossover region, we need the energy calculation or something. Other questions? Okay, so let's